So this is where we ended last time. And I sort of introduced this model differential equation. And this is, we're going to use this for the next few days as sort of the model PDE because, or the model in this case, just differential equation. Because I think everyone should be able to see that if I can solve this guy in general, then if I set, say, C of x equal to 0, f of x equal to 0, and a of x equal to EA, then I can solve the elasticity equation for a bar, right? If I set a of x equal to k over mu, I can solve the steady state diffusivity equation, right? So this is just a generic differential equation that represents, you know, depending on how you choose the coefficients, then it represents several different types of physics. So we'll just focus on trying to solve this guy. And in fact, on your next homework, you'll solve this guy in general. But then if you just turn off some of those coefficients, you have a sort of general purpose ODE solver for this type of equation in one dimension. Okay. So you remember we said we're going to seek a solution U that's approximated by U of H. That's the sum over J. What do I use? CJ, Phi J, where CJ are some unknowns and Phi J are some approximation functions. Okay? So without saying why, let's choose well, I also had this phi 0 term, right, that I said was just consistent with the boundary conditions. So let's choose phi 0 equal to 1. Phi 1 equal to x squared minus 2x, and phi 2 equal to x cubed minus 3x. So again, without stating y at this point, let's just sort of almost arbitrarily choose them, okay? We'll also, to kind of plug some numbers into our differential equation, we'll let L equal to 1, U0 equal to 1, and Q0 equal to 1, I'm sorry, 0. And we're going to let A of x equal to x, C of x equal to 1, and F of x equal to 0. All right? So that means our equation reduces to d dx x du dx plus u equals 0. And if we just use the chain rule to distribute this d dx, then we have du dx plus x d squared u dx squared plus u equals to 0. And u at 0 is equal to 1, and x du dx evaluated at x equal to L is equal to 0. So this is our, after plugging in everything, this is our system now. Okay? So then if we plug our approximations, our arbitrarily chosen approximations into our approximation space, we have that u is equal to u of h in both cases, this should be the real solution u is approximated by UH, which is equal to C1 x squared minus 2x plus c2 x cubed minus 3x plus 1. All right, so all I did was plug these guys in to that, okay? And you can see that it does, in fact, agree with the boundary conditions, right? If x is 0, then the first two terms go away and you just have 1 left. So it agrees with u of 0 is equal to 1. And likewise, the other boundary condition is also satisfied. All right. So let's just compute the derivatives. And if we plug that into our different, so those are just the derivatives, and then we just plug everything back into our differential equation. So that's the right-hand side, and all that's equal to 0. Okay? Is that true? Is the left-hand side equal to 0? Well, you have to figure out if you can choose a C1 and a C2 that make it true, right? So the only way that would be true is if all the coefficients of the powers of x were equal to 0, right? So if we look at x3, we have c2 equal to 0, x cubed rather. X squared, you have minus 3 c2 minus 6 c2 plus c1. That's equal to minus 9 c2 plus c1 is equal to 0. x1 minus 2 c2 c1 minus 2 c1 minus 2 c1 minus 3 c2 is equal to minus 6 c1 minus 3 c2 is equal to 0. And the constant term, or x to the 0 power, 2 c1 plus 3 c2 plus 1 equal to 0. All right, so then the question is, can you choose a C1 and C2 that satisfy those equations? No, it doesn't work, right? And why should it? We just sort of arbitrarily chose those approximation spaces, right? So why should it? So let's see if we can do something different. Let's go back. Let's go back to our differential equation. So it was minus d dx x du dx plus u equal to 0. Now, would everyone agree that I don't change this equation if I multiply both sides of it by something arbitrary? Right? If I multiply the left and the right by 10, does that change it? 11, 12, 15, x? Right? So, well, it doesn't matter if I x squared even, right? Why would it matter if it's linear? If I multiply both sides of the equation by the same thing, I don't change it because I can just divide it out, right? So let's multiply both sides of the equation by something arbitrary. If I multiply it by any function, I don't change the equation. Okay. So we want this statement, we want this to be true in an average or an integral sense. Okay, so not point-wise like the ODE, but true over the entire domain. Okay? So we're going to integrate this over the domain. The domain goes from 0 to L. And we have this del U here. And this is sort of a weighted residual statement. So you sort of have, this is the residual, and this is the weight. And you could write this like W R dx equals 0. Right, so then the residual, if we plug in those same approximations, we know what the residual is. It's what it was before, right? If we plug in those same approximations, we have C2x cubed plus C1 And the reason we couldn't solve that system of equations earlier is because we had 4 equations and only 2 unknowns, right? So if we choose the weights such that they're linear independent, so we're going to choose 2 weights such that they're linear independent. Everyone agree that those are linear independent? Right? There's nothing I can multiply, well, yeah. These are not linear combinations of one another. Nothing I can add to that to get that. Or you can do it by inspection. I mean, what can I add to that to get X? So then we have the integral from 0 to 1, plugging in, remember we said L is equal to 1, of our weight, 1, times the residual, and we integrate that guy. And so now we're integrating this function, okay? Integrating this function from 0 to 1. And what you get is 1 plus 2c1 plus 3c2 So there's one equation. So I'm integrating it over the domain, so the x's go away, right? So then I have one equation. So then I'm going to do the same thing for the second equation. So the second equation is x, second weight x times the residual. And that's equal to 1 That's equal to that. So now I have two equations and two unknowns, and I can solve it. And if I do, I'm just going to write down the answer. If I do, the C1 is 222 over 23. C2 is minus 100 over 23. All right. So with those coefficient values, now I can plug back in here and here, and I have a function that approximates my solution to that ODE, to this equation. So I sort of chose both the approximation, the fees, right, the approximations, I sort of chose them arbitrarily. And also the weights I chose sort of arbitrarily. Right? So what we really want to do and what we're working towards eventually in the finite element method is a systematic way of choosing the approximations and the weights. Yeah.
Did you choose the functions in a way that they satisfy the bound functions?
Could I choose them in a way? I did choose them in a way. Yeah, yeah. That's a requirement. Okay. And what we'll see as we move forward towards the finite element method is that's not always easy if you just sort of choose them arbitrarily like we did. Those happen to satisfy the boundary conditions. But if you, there is a systematic way to choose them such that they will always satisfy the boundary conditions. Right. So I'm just going to